Now we can look at modeling concurrent functionality in VHDL, and this is where we finally start putting everything together and coming up with a model of a digital system that can actually be simulated and synthesized. Now, a big concept here is concurrency. So what does concurrency mean? It means the parallel nature of real circuits. So for example, if I had an AND gate and an AND gate and an OR gate like this, these two AND gates are independent systems, okay? So they will execute, they will compute their outputs independent of each other. So when we go to model that in a hardware description language, we need the ability to be able to say, do this and do this and, but they have to execute at the same time. So for example, if I had F1 is A ANDed with B, and we'll go into the syntax in a second, and then F2 is C ANDed with D. Even though these two lines of VHDL occur sequentially in the text file, they're not executed just like a sequential execution computer. They're not executed like this. The computer doesn't go, oh, I'm going to do this AND first, then the next clock cycle I'll do this. That's not how it works. Is you list these and it is all read into the compiler, and it is then simulated as if these two are identical to each other. And it also will be synthesized as two independent computations, or two independent operations. So that's what concurrency means. And concurrency is important when you're modeling combinational logic circuitry, because if you look at the situation, we need different operations to occur independent of each other and at the same time. So that's what we're going to look at, is we're going to look at some modeling techniques in order to model combinational logic. So the first thing that we need is an assignment operator. So this is a signal assignment operator, and it is this. So it's the less than symbol and the equal sign. So this is the assignment operator, and when this just occurs after the begin statement, it's known as a concurrent signal assignment. So for example, remember we have the architecture and then we have the begin statement. And then if I came down and I started just putting in assignments, so let's say I had F1 and I'm going to assign it, let's say 0, semicolon. So this would be a signal assignment. And then if I came in here and I said F2 gets assigned, let's say A, these two are going to occur at the same time. They are concurrent signal assignments. So concurrent signal assignments. Now, if you wanted to make them not concurrent signal assignments, there's techniques to do that, but we're not going to cover it here. We're just going to look at concurrent signal assignments. Now, this is very important what we've done here, because when I assigned these, I actually assigned I assigned a symbol 0 to F1. There was a couple important assumptions. So number one, when you do an assignment, the target or the destination of the assignment is always on the left of the operator, and then the arguments for the assignment are always on the right. They have to be the same type. So they absolutely have to be the same type, okay? And you can denote different types when you give it the actual value of it by using certain syntax in VHDL. So for example, let's just say I went over here. When I do this, F1 or F2, whatever, gets A, that assumed that F1 had to be of type character. Because if I want to do a character, I can just simply place it like this, and it is interpreted as a character. When I want the type bit, I put single quotes around it. So let's say F2 is going to get 0. I need to put single quotes around it. So that's how you are interpreted as a bit. Notice that if I did this, that is not interpreted as a bit. It will be interpreted as the ASCII character 0. So that's an example of character, bit, character. A couple more examples of this operator are going to be things like, what if you had a vector? So let's say we had a bit vector. Let's say F4 was going to be assigned a bit vector. Let's say it was 4 bits wide. You denote a bit vector by saying double quotes. So I could do that, and that would be a 4-bit vector assignment. So F4 would get 0010. Reals are just handled by putting in the number, so 3.14, no ticks, no quotes. And then if you did have this one right here, I could also give that, this is giving it to it in binary, you could also represent a 4-bit field or a 4-bit value using hex. And the way you do that is, let's say we did this, you go lowercase x and then in quotes you put the actual hex symbol. So this situation would be 0010, that would actually be a 2. If I did that, it would see this lowercase x and then the double quotes on each side. It would interpret that as the binary value 0010. And you can put multiple hex symbols together, so I could do something like this. I could say x and then FA01, and that would be a 16-bit vector. Okay, so that's the signal assignments. Now, functionality, we also need some operators. So we've been able to do some assignments, but we also need some operators. Now, operators are very important, or an important concept of operators is that they're only defined for certain types, okay? So here are your logical operators supported in the standard package of ACL, so obviously not, and, or, nor, XOR, and XNOR. And the way that these works is these are defined for type bit, bit vector, and Boolean. And so I can do things such as I can come along and I can do a signal assignment. So I'd say F1 gets assigned A ANDed with B. And if both A and B were type bit, this would be perfectly valid. If they were type Boolean, it'd be perfectly valid. If they were a bit vector, you would do the AND operation bitwise. So what I mean by that is you would say these two are going to be ANDed together, and it would do it bit by bit. So it'd be like 0, 1, 1, 0. So it's not defined for every type. It's defined for bit, bit vector, and Boolean. Now, when you do these, the order of operation, actually, let's look at the not operation, since it's a singular operation. You put the not in front of the value. So you'd say not C. Okay, order of operation, not goes first, and then everybody else has the same priority. And the way that you explicitly define the priority is you use parentheses. So for example, if I said F3 gets assigned A ANDed with B ORed with C, you would say, well, I want the A ANDed with B to occur first. So you do that, then that would be executed first, then it would take place over here. Then the C would be ORed with A. Now, if you didn't define that, let's say you had, let's do it next, A XORed with C ANDed with B. The way that it works if you don't define it explicitly is that it goes left to right. So it would do this one first, then this one, then et cetera, et cetera, et cetera. So it would work left to right. And so you want to use parentheses when you do this because you don't want to leave things unexplicitly declared or nebulous at all. Okay, so we're going to use these a lot. We can model pretty much all of our logic. But let's look at one other, just a couple more operators for sake of completion here. Numerical operators, you got your plus, minus, multiply, divide, mod, rem, absolute value, and exponential. However, these are only defined for types integer and real, and they are almost exclusively unsynthesizable. And it's a little bit more detailed or complicated to actually get these to synthesize, and we'll look at that later. But these are only defined for integer. So notice you can't do A plus B if A and B were bits, okay? And that's fine because we're just going to model Boolean algebra right now, or combinational logic. Okay, so let's take a look at some relational and some shifts and concatenation really quick, so you're going to have relational operators, so you can do Boolean conditions, equal, not equal, less than or greater than, et cetera, and these are defined for type Boolean, or the output is Boolean. You can compare any two types, but the output's going to be Boolean. You also have a shift operator where you can take a bit vector and you can shift the bits left or right, so it's got a logical and arithmetic shift. And then it also has a concatenation operator in the base package. And what that does is it takes two values and it combines them together. So for example, if I had 1, 1 concatenated with 0, 0, that would form the value 1, 1, 0, 0. So in this signal assignment, I assigned a 4-bit value to bus 1. Bus 1 had to be declared as a 4-bit vector. Okay? All right, so finally we're ready to start modeling some real combinational logic. So there's three primary techniques that we'll look at in this video, and these are concurrent functionality, and we're basically trying to model a combinational logic circuit. So the first one we're going to look at is called concurrent signal assignments with logical operators. So it's kind of a mouthful, but concurrent signal assignments with logical operators. And what this means is that we are going to take some combinational logic circuit that is defined, in its sum of products or product of sums form, and we are going to explicitly list out signal assignments which match all of the operations. Okay. Now we're going to need to do signal declarations. We're going to need to do multiple assignments. But let's just walk through an example of how you can do this. And let's start at the absolute top, and we'll do the entire VHDL file. Okay. So let's start with this example. So let's say that I had a system. Let me zoom out on this. Let's say that I had this system and I wanted to model it. Here's the truth table. It's got, let's define its ports. It's got three inputs, A, B, and C. It's got an output F. They're all going to be of type bit. We have its truth table right here, which defines the functionality. So I want, for all the input codes, I want 1, 0, 1, 0, 0, 0, 1, 0. So we're going to call it systemx. So I'm going to create a file called systemx.vhd. And I'm going to put at the top of it, we're not going to include any extra packages or libraries. We're just going to use the standard functionality of VHDL. Here, I'm going to define or declare the entity. So I go keyword entity, give it the name of the system, systemx, keyword is, keyword port, and then I'm going to list the inputs and the outputs. A, B, and C are the inputs. So they have the mode in the type bit. I can put them on the same line, comma delimited, because they have the same mode and bit. F is the output, so I put it on its own line, colon, out, the mode is out, type is bit. Notice the semicolons here. Notice this last semicolon is outside of the parentheses. End entity. So that's the first part of my design. Now, I'm ready to start modeling some behavior, but the first thing that we have to do is we have to actually synthesize the logic. So this is an example of, it's something that is very useful in VHDL, but you're not really taking advantage of the power of the modeling at a higher level of abstraction, because you're essentially needing to design the entire sum of products logic diagram before you actually put down these operators. But this is just an example. So why don't we do it with a canonical sum of products form. So what I'm going to do is, here's the logic expression that I'm going to implement. So A naught ended with B naught ended with C naught, ORed with A naught ended with B ended with C naught, ORed with A ended with B ended with C naught. So what I'm going to do is I'm going to bring in A, B, and C, and I'm going to invert all three of them and create internal signals called AN, BN, and CN. Those will then be used in three input AND gates and that each represent these minterms. I'm going to create three internal signals called M0, M2, and M6 that receive these products, and then I'm going to OR them all together and drive the output F. So let's look at what the architecture would look like. The first thing in the architecture is you go architecture system X of system X, architecture system X arc. So I actually put in here system X arc _ arc to give it a unique name. And I said of system X. That system X is the entity. Then I say is. Then I'm going to come down, and then the next thing that I'm going to do is I'm going to declare my signals. So I need to declare three signals which correspond to the inversions of the input variables. So AN, BN, and CN, and they're of type bit. Then I'm going to create three signals which are the outputs of the product terms. So I'm going to call them M0, M2, M6, type bit. And that's all my declarations. So I can then do the begin statement. And now I'm ready to actually do some logic. So I'm going to do it with concurrent signal assignments and logical operators. So look at these three operators. all I did was simply say AN, which is my internal signal, gets assigned not A. BN gets assigned not B. CN gets assigned not C. I have now essentially laid down 3 inverters. I put a comment over here that these are the nots. So I got those internal ones. Now let's look at the next ones. I'll move this up a little bit. I'm going to go M0, which is this product right here, is AN, and it with BN, and it with CN. And I've got this one right here. M2 is AN, and it with B, and it with CN. Finally, M6 is A, and it with B, and it with CN. So these 6 assignments now are ready to produce the final assignment, which is M0 ORed with M2, ORed with M6, and that's the output. End entity, and that's it. So my file would contain the entity and also this architecture. This would be a simulatable, synthesizable model for this truth table right here. The technique I used was concurrent signal assignments and logical operators. Okay, so we kind of said that is a really that's a way to model logic that doesn't take advantage of any of the automated synthesis tools. We still had to create the circuit using a classical digital design approach. So the next one we can look at, so this was the first technique we looked at. The second technique we're going to look at is called a conditional signal assignment. And this is where you can take advantage of describing just the behavior in VHDL of the system we want, and then letting the CAD tool itself actually synthesize the final logic. Okay, so the way that you do this is you're going to use these keywords as follows. So what you're going to do is you're going to do a signal assignment. So you're going to say whatever the signal name you're assigning to, and it's going to get something, some value, and you're going to use a keyword when, and you give it a Boolean condition. Then you can say else, and you can list out what it would be assigned to when another Boolean condition. And you can continue this until you've explicitly listed or implicitly listed all possible input codes and what the actual output was, and then you end it with a semicolon. So let's look at a quick example of that before we implement our same circuit. So here's what it would look like. So I could say F1 gets 0, keyword when A is equal to 0. So this right here is the Boolean condition. So this is a Boolean condition. Is it true or is it false? So when it is true, it will get F1 will get assigned 0. If it's false, it will then go to the else clause and it will assign it a 1. So that's an example of it. Now, this is a very simple one. You can form these together to make more complicated assignments. So for example, I could say F2 gets a 1 when A is equal to 0 and B is equal to a 1. Notice I can use a Boolean operator within here, and I can put optional parentheses, but it's when this statement is true, this assignment will be made. If it's false, this assignment will be made. Okay. You can also do signals. It doesn't have to be an actual value. So for example, you could do F3 gets A when this, else B. So it doesn't have to be actual logic values. Okay, so let's go back to that same example. So here's that same truth table, and I want to implement this with a conditional signal assignment. So my entity is going to be identical as before, and now take a look at how we're going to do this. Architecture system X arc of system X is, we don't have any declarations, we are simply going to begin, and look what I'm going to do. I'm going to say F gets a 1, and what I'm doing is I'm describing the first row in the truth table. When this Boolean condition. And the Boolean condition is simply A is a 0, B is a 0, and C is a 0. So that represents when the inputs are all zeros. Else, I'm going to go down and say give it a 0, and this represents the row 1, and that's when A is a 0, B is a 0, and C is a 1. Else, and I can simply repeat this throughout all 8 possible input codes. So look at this description right here. It's a very readable, it's very descriptive, but we didn't tell it whether to use AND gates, OR gates, whatever. We just described the functionality given in the truth table. So we're finally at a point where we can take advantage of the abstract modeling capability of VHDL. Now, if you look at this, you might notice that this else clause could be used to your advantage to make an even more compact representation. So I could have actually said, I could have just said, I want to only list out the ones. So I'm only going to list out the conditions when the output gets a 1, and then I could use an else clause to say, otherwise just give it a 0. So these are identical to each other. One of them is a little bit shorter in terms of syntax. One of them is more verbose, but probably more readable. So this is almost a direct mapping of the truth table. So that's the second concurrent signal assignment, or concurrent modeling technique. Okay, so the third one, we have 3 of these now. The third one is going to be what is known as selected signal assignments. And this gives even an even more compact way to model combinational logic. So the way that you do this is you use a keyword with, and then you give it the input name, so what input you're looking at, and then you use a keyword select. Then you say the output is going to get assigned some value when a condition, and then comma. And the way that this works is, if this condition's true, it will assign this expression. If it's false, it will go then to the next condition and say, when this is true, assign this. And you can cascade these decisions and these expressions all the way down to the point where you're done. And you also are provided with an others keyword, and that's kind of like the else clause in this. So let's take a look at how you would do that. So here's an example. With A, select. Okay? So when A is a 0, F1 gets 1. If that's false, it goes down here and says when it's a 1, it gets a 0. So that's an example. It's comma delimited, and the way you save space is that you don't have to actually list out what the input variable names were. You just simply list it once up here in the with syntax, and then you can just list its value here. There's one catch to this, though. You have to only have one signal name. So that means if you had a system that had 3 input scalars, you have to concatenate them together before you actually use it within this. So let's take a look at how you would do that. So I'm going to look at that exact same example that we just did, and we are going to implement it using selected signal assignments. So the first thing you notice, architecture, or the entity is identical. Architecture, we now do have a signal declaration because I need some way to concatenate my 3 scalar inputs. So I'm going to create a signal called ABC, and I just made that up just to, it's kind of related to the ABC scalars. And I'm going to give it a type bit vector, 2 down to 0. And now that is a 3-bit vector. I say begin, and now I can simply do this. I first need to concatenate to assign to this new signal that I created. So I say ABC gets A concatenated with B concatenated with C. So now I can do with ABC select. Notice that this with ABC, it had to be one signal name, so that's why I had to do that concatenation. And now I can just say F gets a 1 when 0, 0, 0. So that's representing the first row in the truth table. If that's not true, give it a 0 when 0, 0, 1. And then give it a 1 when 0, 1, 0. And you simply list out the entire truth table. And you now have a very compact way to describe the functionality of this circuit. Notice that it's a little bit less syntax than a conditional signal assignment. You did have to do the trick with the concatenation if the input wasn't a vector, but it's a very concise way to do it. Okay, you can use the when others clause to even get more compact. So look at this example. I simply said I only list the cases for when it's a 1. So I say it's a 1 when 0, 0, 0, when 0, 1, 0, and 1, 1, 0. Otherwise, it's a 0 when any other input code. So this is even more compact. Then the selected signal assignment actually gives you an even more compact way to do it by pipe delimiting the inputs. So for example, you go F gets a 1 when 0, 0, 0, and then this is a pipe. So it's pipe delimited. Or it's like saying 0, 0, 0, or 0, 1, 0, or 1, 1, 0. And then you use the others clause to pick up the 0. So that's 3 different ways to do selected signal assignments for that same truth table. Okay, so now what we have is we have 3 modeling techniques to actually get a simulatable, synthesizable combinational logic circuit. Concurrent signal assignments with logical operators, conditional signal assignments and selected signal assignments.